Hello, everyone. My name is Krzysztof Kudryn, and in this presentation entitled Traditional and Deep Learning-Based Vehicle Autonomy, I will be talking mostly about traditional and deep learning-based vehicle autonomy. Surprise, surprise. The field of vehicle autonomy is quite huge, and covering everything in half an hour for both deeply technical people and absolutely non-technical people here would be a joke. But we are not going to laugh. We are actually going to do it. And here's how. We will start with a short overview of the components of vehicle autonomy, so perception, localization, path planning, and control. We will analyze traditional implementations, their algorithms, and video demonstrations. Then we will see where and how deep learning is taking over this field, from comprehensible introduction into deep learning concepts up to examples and demos of either my own hobbyistic projects in this field or professional projects implemented by either me or my friends in NVIDIA. So, in autonomous driving, the most commonly listed components are localization, perception, path planning, and control. The role of localization is to say where I am on the map, and although localization is science in itself with huge amount of different scenarios possible, for most cases, its theoretical backbone is the same. It's the bias filter algorithm. And if you are not familiar with this mathematical masterpiece, I hope you will enjoy my own intuitive explanation of how it works later on, so don't worry. Perception is how the machine translates signals acquired by its sensors into interpretable representation of the environment. And most important sensors here are obviously cameras, single, multiple, or LiDARs, so laser sensors measuring distance and usually rotating. And to interpret all that, we have a wide range of algorithms in computer vision available. Path planning is too wide a topic to even give a sensible overview. It ranges from routing algorithms, from taking you from A to B, through local scope objectives such as velocity keeping, up to maneuvering in dynamic scenes and collision avoidance. So in other words, after perception and localization, you know where you are and what's around you, and the aim now is to navigate through that to your destination in an optimal way. Optimal in terms of safety, in terms of time, in terms of user comfort, and obviously acting within traffic regulations. And finally, the control is what low-level commands you need to apply to your vehicle actuator so that you actually follow your desired trajectory. And here the fundamental equation would be the PID controller. And the applied control here is a function of error versus desired trajectory. And P in PID stands for proportional, which means, well, in the beginning, there is a big error, so we will intensely approach the desired trajectory. But as we move closer, the error gets smaller, so proportionally we applied smaller control. But as you can see, you can never attain this trajectory this way. So to fix that, integral control, so I in PID is applied. So we are also integrating this error. So it is accumulating, and we can add it to our control. And this way, we can finally attain our trajectory, but we can also, as you can see, overshoot a little bit. And that's why, to fix that, we can calculate derivative of the error, so D in PID, which makes us control the rate at which we approach our desired state. Simple in theory, but in practice, usually we have no direct control over our trajectory. We cannot apply 2 meters to the left. We can apply 20 kilowatts change to our engine or 2 degrees change to our steering wheel. So this is a very indirect approach, and to be honest, finding a stable PID solution is a complicated engineering task. So that would be overview of the components of vehicle autonomy most often encountered in literature. We could modify it slightly by changing the perception to be at the first place, and then localization and path planning, because they all need perception anyway, but that's just a detail. Now, let's analyze some practical examples so that we can dive into algorithms with more intuition. For a start, a hobbystic drone project delivery, which I realized some time ago with my friend. Suppose we have an indoor map of some factory or an office, and we would like the drone to deliver a cargo from somewhere to another place. So the drone needs to localize itself in this map indoors. It doesn't have GPS, anything like that. And it needs to fly to pick up the cargo and then fly to another destination and land with the cargo. From perception point of view, drone has a camera directed downwards, so actually it sees the floor, and some set of standard sensors like accelerometer, gyroscope, and height sensor. So how will the drone know where it is on the map? It will use bias filter algorithm, and more precisely, its flexible implementation called the particle filter here. Now, I realize not everyone here gets thrills of the excitement when seeing this beauty. So instead of diving into the maps, I will tell you a story. So we could name this story a particle filtering story, but in fact, this will be a story that could happen to you, to me, to anyone else in this room. And for the reasons that will soon become clear, we will call it a hangover story. So let's imagine this day when you wake up and you are trying to realize where you are. And you are yet too afraid to open your eyes, but in your imagination, you are trying to mark all the spots where you might actually be in according to flashes of your memory. And your first prediction is not very satisfactory to you, so you finally decided to open your eyes and make your first observation. And from what you see, you know you are not drifting in the ocean. So the places at the ocean disappear. You must be somewhere on the coast or near the big lakeside or a very big river. But you decide to walk, and you walk for a long time, you walk kilometers, and what you still see is the beach. So you can no longer be anywhere inland. You must actually be on the border for sure. So you walk along, and you see two soldiers guarding their passage, and you know immediately you are at the border. But the guys have guns, so you turn away, and you walk with the sea on your right-hand side, and you finally are able to make your final observation. You see a tourist, and you know immediately you are in Poland. And that is particle filtering. So how can we apply this to our autonomous drone? Well, like in our hangover story, the probability distribution of where we are is represented by these red particles. And first, we move all the particles according to the readings from our sensors. And then for each new place, we check how probable it is by comparing, by correlating what the drone sees with its frame and what it should see in these places from the map. And the places with high correlation get more density, and the places that have no correlation disappear. And that's how we iteratively, recursively apply positioning. So first, let's see how this technology works for the prototype of map creation. So what you can see here is the drone flying inside the office with books scattered around the floor. On the right in the middle, you can see what the drone sees with its bottom camera. So basically, you see the floor. But after calibration, these camera frames will be added to the map, which will be created on the left-hand side while we fly. So first, the first frame will be added, and then we are localizing, simultaneously localizing this map and mapping the region. So while we fly, there will be these particles all the time will be updated, and only in the places where there are highest probability where we are, the frames will be added on, and this way we will be getting a map. So to our particles, we apply our sensors, and then we verify the probability of this position by correlation. That's how we are creating a map. Now, the map all the time gets updated, but just for fun, in the top now, you will see what the drone sees. We are in the office. So we got spotted, so we hide behind the wall, and we continue the mission in the enemy territory. So that's world-class autonomy, guys, you know. But what is interesting also here, all the time the map gets updated while we fly, and in a second you will see it because we will fly over the desk, which was previously seen from the side, and now we will see it from top. This is a top view map, so it gets automatically updated. And we get the smooth map. And the system knows where we are on this map, so we can just select a target, and the PID algorithm will take over the control from us. In fact, we don't know exactly where we are. We have our particle filtering approach, but we can apply PID to every particle and then just apply the resultant, okay? So, coming back to our mission, the drone will wake up, not knowing where it is. It will go to target 1, it will pick up the cargo, then go to target 2 and land with the cargo. But before I continue with the demonstration, which I hope you already cannot wait to see, I have to tell you something. Although this was a hobbyistic project, together with my friend, we are professionals. And as professionals, you know you need to have a certain plan of actions. So first you buy the drone, you open the box, you learn to fly manually, you gather some characteristics, and then step by step run your development and test cycles to design your project iteratively. However, at the same time, we are enthusiasts. And as enthusiasts, we started with a final design. Then we bought all the electronics that came into our head, and then we bought the drone. We immediately rushed with the development, and it was going really, really great. After celebrating first successful version of our software, we finally decided to open the box. The drone was inside, so we added all the electronics, and we gloriously went for our first test in the field, which turned out to be the last test of our first drone. With the next drone, we decided to learn to fly manually first, and then continue with almost professional approach, you know. So you can see we struggled a lot, but I hope that this demo of the prototype of the indoor cargo delivery system will leave you with no doubt that it was actually worth it. So let's go with it. There is much lag in this video. You will notice it later on because we have some problems with communication. But nevertheless, after calibration, we will start our global localization, and you will see on the map the particles will converge very quickly from all around to the place where we might probably in. There is actually a small bug here, but it doesn't matter for this demonstration. And when we know where we are, the system will take over the control, and we will fly to target number 1, where the pickup mission will be performed. Now, this was just a prototype, and the drone got a little bit lost, so it will take some time. But I will use this time to tell you about our pickup technology, which is not yet patented, but it considers of a magnet hanging on a sticky tape, you know? And sometimes the magnet goes into pendulum motion, and it obstructs the view of the height sensor, so the drone does not know how high it is. You will see how the drone deals with that later on, which will be very interesting, I hope. But now, I think we can focus on the pickup mission, because soon the drone will see the cargo, and it will find itself. Okay, it sees the cargo, so it wants to pick it up now. So yes, here's the pickup. Here's the misjudgment of height. But we are flying towards target number 2, and we are landing. We are landing. We are, well, misjudgment of height again. Conclusions. We broke the glass. We broke the drone. We displaced the ceiling. But we managed to localize ourselves. We went to target 1. We pick up the cargo. We went to target number 2, and maybe not too smoothly and not in the right place, but we delivered the cargo to the ground. So, Thank you. So, judging from this, you can see this hobbystic project of our indoor drone delivery system was clearly considered a pure success. But putting jokes aside, and putting aside the hobbystic stuff for a moment, let's see how autonomy is professionally applied in self-driving cars. And let's begin with localization. So let this dot be our car. And now we need to properly switch between a few coordinate systems, like internal car coordinate system, which hosts our sensors, road coordinate system, local reference system being a Cartesian approximation of projection of the global reference system, which hosts our map. Yes, it's quite complicated, but it is doable. Unfortunately, car is not a dot, and the car with sensors mounted on it is not a dot. And considering the centimeter level global accuracy which we aim for, even things like contraction of suspension is really significant here. It's significant that every wheel turns at different angle in the car, in fact, and that there is a drift also. So keeping track of every parameter here in our particle filter would make it go crazy. And in fact, most of these parameters are either approximated or solved later in post-processing. So with that assumption, you can say that our car is like a 6-dimensional Euclidean space point, which is okay. And then we can have our particle filtering, like we can see here. So we have our position as distribution of brew particles. And now we perform our movement update of our particle filter with the sensors in the car, like odometry. And then for each point, we check how probable it is, not with the drone photo versus the map, because it's not a drone, but with the point cloud of key points, which is observed by our car, and how it correlates to the point cloud, which is available in the map previously. So this would solve localization, but the question we have is, how do we solve perception in the car to get these point clouds? Okay? And the first, key points can be obtained from camera images. Camera images, 2D camera images, will give you 3D key points. How? Well, what you see here is some example setup of fisheye cameras mounted around the car, visualized in DriveWorks, which is autonomous driving framework developed by my company. And with such setup, there are many ways to derive point cloud, but in theory, only one camera could be enough. One camera only. To prove that, let's focus on the door handle in my room and the glass. And as you can see, while we move, the glass, which is closer, moves much faster than the door handle, which is far away. And in fact, we can use some kind of technology like optical flow of pixels in the image, and we could get some information about 3D space here. A better, more sophisticated approach is called structure from motion, and the principle is quite simple. Here we have two images of the same object taken in different perspective, and as long as we are able to identify some pixel, which is the same pixel in both of these images, well, this pixel have to satisfy geometry, and if we can find at least seven such points, we can form a set of equations, and we are able to both reconstruct the object which we are looking at and also the displacement of the cameras. And obviously, to prove that, I actually coded the algorithm myself, and I recorded a chair in my room. So again, sharing my privacy here, I hope you appreciate that. So at every frame, key points are identified, they are related between each other, solved in 3D, and added to the visualization. So as you can see, from a photo, 2D, we have a 3D visualization, no problem mathematically. Structure from motion. And when we have more cameras like this with known displacements, well, then the solution is even more stable, obviously. But instead of this, or in parallel to that, we can have direct point cloud from the LiDAR, for example. And you can see its points, the point cloud being generated at the moment in the visualization. And if you look closely, you can see smear of points going together next to us somewhere. And these are actually cars. So this is how we detect cars, while other static points will be used to correlate us versus the map. And with that, we can plan our path to meet the map constraints. As you can see now, we know where we are, so we can move in a way to follow only drivable lanes. And we also see other cars, and we can adapt dynamically to that with our path, which hopefully completes the overview of self-driving car autonomy. And we can finally move to numerical optimization. I mean machine learning. I obviously mean deep learning. I mean artificial intelligence. So obviously, we start with perception. So here, among other things, we want our intelligent car to look at the other car and know it is a car. In other words, we want a car detector, which would say, looking at this image, then there is a car somewhere detected inside this image. And very importantly, we want it to say there is a car only when there is actually a car and not something else. So this is so easy. Why do we need artificial intelligence? Let's have a quick traditional analysis first. So for simplicity, let's pool our car into some lower resolution. So we apply pooling. It is quite aggressive, but if you shade your eyes, I hope you can still see a car. Of course, it's only illustration with all three channels just artistically mixed in a single image. But nevertheless, let's normalize values to lie between -1 and 1. And now let's try to detect a window here. Yeah? How would the pattern for a window look like? Well, we have two windows here, and they are both white dots enclosed by some red stuff. So the pattern for a window would look like this. How do we find correlation? Well, if we wanted to detect window here, we would just apply pixel-wise multiplication between the two, and then we will sum it up and have some value. It will be very small in this case. But if we do it here, it will be very large number, because when we multiply, all the values are of the same sign, and therefore all of them positively add to this matrix, and the result is high. And if we slide this window over all image, which is called convolution, we would have a response which is high only in the places of windows. So that's perfect, we detected windows. But hey, why do we detect windows? I have a much more brilliant idea. With a single convolution, I will detect a car. How have I done this? Well, here's my pattern. I convolved my image with the pattern of the car, and I get the response. It's also a good response for the dog, because it does not detect a dog as a car. But unfortunately, for other cars, it misses a detection, because that's not this car. Well, come on, that's obvious, no? It does not correlate. But if you look closely, it correlates a little bit with the car in two places, like here and here, because the wheels correlate more or less with each other, the windows somehow correlate. So maybe, in fact, if we detected wheels first, then windows, and then combine that everything, maybe we would have a nice solution. So let's come back to our previous idea. We pool our image again for a lower resolution, for better generalization. Then we define a window pattern. We convolve this with a window pattern and put everything in a blue channel. So now windows are detected as blue. Then we define a wheel pattern, something that is similar to wheel in this image. We apply convolution and put it in a green channel. And finally, we detect car body pattern, create car body pattern, convolve that, and put in the red channel. If we now do again the same thing, so we pool ourselves to even lower resolution, what you see here is like a generic description of the car, which has windows somewhere on the top, has wheels somewhere at the bottom, and in green and in red somewhere a car body in between. And we can find a pattern that would fit all the cars now. It will look like this, and if we slide convolution through that, we'll have a very high response somewhere in the middle, because it's a car. Yes, it is. So we now have a two-layer detector which detects a car. And it does not detect dog as a car. And for different cars, it starts to have some reasonable detection. Of course, this car is not red, but you can imagine we could solve this by creating a little bit more of filters, also red filters. But then, still the wheels might have different rims, no? Windows can be a little different shape. So similarly, here again, we could put everything into even lower level of abstraction and split it to detect more primitive features first, like arcs and so on. And as you can see, if we even add some more rectification layers to make it even less symmetric, now we can have a very nice detector. So can anything go wrong now? Oh yes, to our deepest disbelief, it might turn out that the world is not flat. But we can probably, even for such perspective, craft some more filters, like skewed edges and combinations of that into like elliptic wheels, which would better detect this car here, and we will be fine. But then one day, a car without wheels will turn up. And well, we can still some craft filters for detecting all kinds of lights, bumpers, and who knows what else. And finally, we will, after looking after tens of examples, we will realize we are really tired about this manual thing. But summing up, we have a promising solution which layer by layer detects higher level of abstraction of the car until finally it finishes with a big number if there is a car or 0 if it's not a car. We can easily turn this into probability of detection of the car by adding normalization like softmax function. And we showed it can work. It can work, but manually applying all the filter pixels is like really tiring. And here comes the optimization algorithm, turning this unspectacular architecture into artificial intelligence. I'm telling you again, this is just optimization algorithm that will turn this unspectacular architecture into artificial intelligence. You all know optimization, I hope. So we have just a few training examples here with just a single feature, x1, and a value. And now we would like a model to approximate this example, one-dimensional model. Why? Because we only have a slope as a single parameter, and then we calculate the cost for that, for example, mean squared error. It is huge, this error, so we calculate its derivative, and we can go down the gradient until we finally find a slope with minimal cost. In mathematical frameworks, it's just one line of code for this simple example. In our case, our example is not one-dimensional. It is actually total number of pixels dimensional, so it's like 10,000 of dimensions. Our model is not a single slope parameter. It is total number of pixels in all the filters dimensional, which is like 100,000 of dimensions. Our loss is not a mean squared error, it's cross entropy here because it's a classification, and we need a bit more than just 6 examples. We like enormous training data set to train that. And the science behind such huge optimization is huge. But in mathematical frameworks, it's just one line of code. So here we have an implementation of that solved manually again. So we crafted all these filters, a few layers of that to detect a wheel of the car. And with such primitive manual solution, we will have accuracy of, let's say, 55% maybe. So only a little bit better than random. But if we put random values here and provide training examples and the machine optimize the same model for us, starting from some random values, it will go into the solution that will reach around 80% for this small model. But we no longer need to manually put all the pixels by ourselves, so we can do a big model because the machine does not get tired of doing that. And then we can observe that the machine crystallizes solution beyond any handcrafted design, being 99% on the validation test set. So we've trained a binary classification network, but we can easily add more classes very easily. And although everything looked so easy here, to be honest, in practice, building a good model needs experience. And it is often a good idea to use architectures which are proven by the data science society, and there are papers about it, like ResNet 50 classification network, for example. Then detecting objects in image is also possible. You only need to plan well your architecture first, and then craft a little bit more elaborate cost function for that, or you can use proven networks such as single-shot multi-box detector like SSD, and also segmenting image is also possible. You only need to add upscaling layers to what you have in our network and properly plan your cost function again, or you can use proven networks like Mascar CNN or UNet or so on. And having all that, we can see how this works together when applied for vehicle autonomy. So you can see segmentation network is used for road segmentation into separate lanes, and an object detection network is used to detect various objects, like cars, like road signs, and so on. So basically, we have just replaced whole visual perception of vehicle autonomy with only deep learning. And the question you might ask now is, can we do this for everything at once? In other words, can we design a network that will learn steering signals directly from sensors, like cameras? And it turns out it's a valid experiment. It's a valid experiment, and there has been quite successful attempts to realize that, and they are documented in the literature. However, please remember, this is just optimization algorithm. So it depends on the data you give to it. And yes, with enormous data set, you might be able to train it. You might be able to train it, but it's impossible to cover all the corner cases. And also, it is so easy to fool such a network. By the way, deliberately cheating a network is, if I'm correct, the topic of the next presentation, but this is for a big network, it's even easier to cover all the things. So it's definitely safer to avoid that by controlling smaller components separately. And finally, also components like PID controller or a bias filter are still doing a really good job at solving their tasks, so there's no need to throw them away and replace them with deep learning. They are really good. But now, awaited by everyone in this room, David Hasselhoff and his talking car. That's it. It talks, and it knows what it is talking about. And it can describe its environment better than Eliza Orzeszkowa-Niemen. Fiction? I wouldn't say so. In the recently popular concept of human-centered vehicle autonomy, AI does not decide on its own. It is just supporting human in their reaction times and bringing control to a different level of abstraction. Like before, the car builds its understanding of the external environment using computer vision networks like ResNet, SSD, Mascar CNN, or UNet. It also monitors the interior of the car, and it communicates with the driver about this either via visualizations or with speech, by talking to them, using networks like GNMT, Transformer, or BERT to translate its knowledge into sentences, and then to make that a speech sound understandable by human using networks like Wavelo or Tacontron 2. Now, if you are interested about the details here, implementations of all the network architectures that you can see here are actually optimized for enterprise usage by me and my teammates from NVIDIA, and are available to download via NVIDIA NGC, which I strongly encourage you to check out. But state-of-the-art way of proceeding with vehicle autonomy and robotics nowadays is to first train networks with huge amount of GPU processing power, allowing quicker training cycles, and using novel automatic mixed precision approach for even better performance. And then, having produced a model with this complicated software and a very high computational expense, we build an inference engine taking advantage of int8 or int4 precision, enabling extremely efficient action with the same level of accuracy, but on devices with limited resources, like autonomous vehicles or robots. Which brings me to conclusion. So the field of autonomous vehicles is huge and exciting, and we only covered a few branches today, but we clearly see that the influence of deep learning is growing rapidly, and who knows what might happen. But As a last thought, I would like to leave you with something else. Does anyone know what that is? Okay, the top at the cross at the top is what the person is looking at, and the cross at the bottom is what the machine generated by analyzing their brain activity. More examples here. To me, it is quite disturbing. Maybe it is not a fully deserved reading in your mind yet. But it is clearly a first step already tested and documented in the literature. So soon the machine might be able to read your mind, and it will learn anything you want. Basically, it only needs you to give it an optimizing cost function. So whether you design it for driving a car, saving the planet, or just winning a board game, please remember to double-check two things. First is to set the cost of human life to infinity. And second is to check if infinity is properly implemented in your environment. Thank you very much.